Okay, so let's talk about another defect. Okay. Acha. In case of another defect, what can happen? First, what we said in Schottky-Wagner defect, the cations and anion will move away from the lattice layer to the surface, to the bulk. Now there is another defect. What can happen? Here, let's say in same MX type of crystal, 1:1 lattice. Okay. Let's say something happened. How happened? What happened? Later. Something happened. Due to this something, let's say this cation. Okay. Due to this cation, okay, let's not talk about cation. Let's say this anion. Okay. This anion moved into an interstitial region here. See. Okay. This anion moves into an interstitial region in the lattice. Okay. Think it very carefully, because interstitial region means let's say if you have this lattice, let's say this is your atoms, these are the atoms. Interstitial region means the voids. Talk about the first voids. Okay. Now this will help. Okay, keep this in mind. Okay, this void. So this void region, in this void region, your, let's say this cation is migrated to this void region. Okay, it can be here also. So this is a random. So there is no hard and fast rule. Okay? It's a random. Anion is moved into this region. So what will happen here? So here will be an anionic vacancy. Anionic vacancy will be there, and your anion is beautifully stayed in here. Okay. Now these kind of defects, okay, these kind of defects are known as Frenkel defect. Frenkel defect, okay, and it has been observed that these Frenkel defects is observed in case of highly covalent compounds. Now next question is why. Why in case of highly covalent compounds this is observed? So what is happening here? The cations, it can happen with cations also. They leave their normal sites. They leave their normal sites and go accommodate in the interstitial sites of the cations and anions. Okay, and due to this, the defect is observed. This defect is known as Frenkel defect. Now next question is why it happens in case of highly covalent compounds? Because there is a reason. Same flow chart. Okay. Now what happens in highly covalent compounds? Highly covalent compounds. So it's covalent. Covalent means the two atoms are sharing electrons, forming a bond. Okay. So electron is shared. So there is no electrostatic interactions. Okay. So it will be a low lattice energy. Okay. So low lattice energy. Low value of lattice energy. True. No, very simple. Low value of lattice energy, comparatively low. Achha. That means if the lattice energy is low, then the packing will be inefficient. It will be inefficient packing, right? Now if inefficient packing, okay, that means your R plus is less than R minus, right? If inefficient packing is there, then the radius of cation will be lesser than radius of an ant. That means what is suggest? Your radius ratio is very much low. Right? Radius ratio is low. Now, if radius ratio is low, then your coordination number will be also low. Radius ratio is low, then coordination number is also low. And if coordination is also low, then what will happen? There will be a high gap in interstitial region. Okay. Now, if the coordination number is low, then there will be a gap in the interstitial region, and due to this interstitial gap, and you have an inefficient packing. So what will happen? The atoms can migrate to the interstitial region. So what will happen? Migration. Atom will go to the migration. Now this effect is known as the Frenkel defect. Okay. So once again. So what is happening in some case of crystals which is undergoing the Frenkel defect? What happens? The cations or the anions migrates from its normal sites to the interstitial sites between the other lattice points. Okay. Now this is observed in case of the highly covalent compounds. Okay. Why? Because in case of highly covalent compounds, the lattice energy is low. Now due to the low lattice energy, there will be an inefficient packing, and which leads to the radius of cation is lesser than radius of anion. Okay. And then leads to the lower value of radius ratio, which leads to also next the lower value of the coordination number. Okay. And this lower value of coordination number leads to a gap. If coordination number is low, then there will be a big gap, that is a void spaces in the interstitial region, and if there is a gap for stabilization, the atoms will migrate to that particular place, leading to the Frenkel defect. Okay. Achha. Now there is 2-3 important questions. Okay. In this this two in context of these two defects. Okay. So I will add that in the assignment. Okay. So you guys just solve it and let me know. Solve it and submit it. Okay. Many very important questions. Okay. Like there is one important question I would like to mention here. I will not discuss here, but a question I like to mention. You think about it. Okay. Question is that when NaCl, just common table salt, sodium chloride, is kept in sodium vapor. You have a box of sodium vapor, vaporized sodium, and you kept sodium chloride. So what will happen? It forms yellow color. A yellow color appearance is observed of sodium chloride. Yes, yellow colored appearance of white. It's important. I will add it in your assignment also. So think about it, that when sodium chloride crystal is kept in a sodium vapor, okay, yellow color colored is observed on sodium chloride. Why? Yes. Okay. There is another question also, is that I will add that in assignments also. So, but this is very important because this question came many times in your ISC and CBSE exams also, and they ask this very important question. Okay, I need you guys to find out the answer, okay, and write it in the assignment and let me know. Okay. So next we will talk about is extensive defect. Extensive defect. Acha. This extensive defect is also known as impurity defect. Also known as impurity defect. So both are same terms. So you don't need to be panic. Both are same terms. So this impurity defect is basically, let's say, if you have a, think very simply. Impurity means you have a pure substance, you add some impurity there, which are the foreign particles which are not characterized. Let's say if you have a silver plate, silver lattice, you add mercury. So mercury is the impurity in that silver because it is it's a foreign particle relative to that silver plate. Okay? So let's say I'm giving you an example. First example, let's say your silver chloride crystal. Okay. Achha. Another thing, adding impurities to the pure substances is known as doping. Okay. Crystal is doped with cadmium chloride. Very nice question. I will start with first example. Silver chloride is doped with crystal, doped with cadmium chloride. Okay, what will happen? If I draw what will happen here? Okay, so see, silver is unit charge, unit positively charged. If I dope with cadmium chloride, which is a dipositive ion, is a monopositive and a dipositive ion. Okay, if I dope with a dipositive ion, what will happen? It will, to maintain the electroneutrality, what will happen? It will replace 2 silver from the surface. It will replace 2 silver from the surface, and what will happen? The resultant structure will be like this. Resultant structure, here will be a cadmium plus 2 and here will be a cationic vacancy. Clear? So what is happening here? Here the 2 silver chloride, to maintain the electroneutrality, 2 silvers are replaced by cadmium plus 2. 1 cadmium goes to the 1 silver side and there will be another cationic vacancy. Right? Now in this system the electroneutrality is maintained, but there will be a vacancy, cationic vacancy. Okay, and due to this vacancy, what will happen? Due to this vacancy, you will observe different properties of this material. Now this material is now active, will show some properties. We will discuss later what kind of properties it will show. Okay. See, another thing here is that in these kind of defects, you see, if I calculate the stoichiometry, means it's a total mass. If I calculate, in this case, the mass will be unequal. That means the stoichiometries are not equal, right? So this kind of defects are also called stoichiometric defect. Okay. So there are another also few questions, like first question number 1. Another question like this is that one question, that silver chloride is crystal is doped with cadmium chloride. Okay. There is another question also, like ZnO2 lattice is doped with calcium oxide, and number 3 question is NiO lattice is doped with Li2. So if you replace, so I am repeating once again, if you replace this, if you dope silver chloride with cadmium chloride, so 2 silver will be replaced by 1 cadmium followed by 1 cationic vacancy. Okay, and this material is electrically neutral, but this material shows different kind of property that I will talk later. Okay. Now this kind of effect is called impurity defect or extensive defect. Okay. Achha. So there is another kind of thing you can observe also. Okay, I need you guys to find it out and write it down in your assignment copy. Is that zinc oxide lattice is doped with calcium chloride. Calcium oxide. What happens? And nickel oxide lattice is doped with lithium oxide. Okay, these 2 questions. Okay. Achha. So till now, what we have talked about, still last lecture, last video and this video, is that the impurity effect, the defects in the first we talked about the Schottky effect, Schottky Wagner defect. What happened there? Here this cations and anion from their normal sides, they goes to the bulk. Okay, and to maintain the electrical neutralization, equal number of cations and equal number of anion migrate to the bulk. Okay, what happens in case of Frenkel defect? Achha, first of all, Schottky Wagner defect is observed in case of highly ionic compound. Okay. Achha, the Frenkel defect, what happened in the Frenkel defect? Where the cations and anions from their normal sites, they migrate into the interstitial region. Okay, and those are observed in case of highly covalent compounds. Achha. So, and what happens in impurity defect also? Here, if you dope a silver chloride with cadmium chloride, okay, the 2 silvers are replaced by 1 cadmium, okay, due to the maintain the electric neutrality. And to maintain the electroneutrality, 1 cationic vacancy is observed. Now due to this, although the material is electrically neutral, this cationic vacancy, due to this cationic vacancy, this material plays very important roles, shows very important properties. Okay. So this kind of thing observed in other 2 cases also, which you need to write it down. What happens? Figure it out. Zinc oxide lattice is doped with calcium oxide, number 1, and number 2 is nickel oxide lattice is doped with lithium oxide. Okay. So next lecture, what we will talk about is the what properties this kind of material shows. Okay, and their applications and all the electrical properties, chemical properties, and next we will talk about the magnetism and finish this chapter.